I was still stuck in behaviorism, and but of course, since you're all experts now on this important topic, we can sort of move through that a bit more quickly. In the meantime, I hope you all have been reading the accompanying chapters in the Living Machines Handbook, because as you might see from that, I try to build up to a discussion we will have towards the end about how you would think you could build a living machine. And the handbook chapters should be helping you to get some background information on that, okay? So last week where we ended, where we ended was in the work by Ivan Pavlov, right? And Ivan Pavlov discovered completely independently by being very observant, right? And I also shared with you last week the dictum of Louis Pasteur, like divine providence favors a prepared mind. And this was definitely true for Ivan Pavlov. So he saw that adaptation and learning took place, and he then posed the question, actually for the first time, how is this done physiologically? Okay, and not only posing the question, because also his mentor Sechenov was already thinking about that, but knowing he could approach it physiologically, that he started to have tools and methods to approach it physiologically. So that was Ivan Pavlov. Now on the continent, we have two things cooking, right? We have the structuralism, which is emphasis on human experience and human performance, right? Especially performance, very critical in this field of psychophysics. And then Ivan Pavlov, more or less on his island, developing this physiology of learning and classical conditioning. Now, what was happening in the States? You have discussed already Thorndike, Tolman, Skinner, the behaviorists, and so on. But I want to recap that history a little bit quickly. And an important transition here, if you want, from the 19th century into the 20th century study of behaviorism is also this proposal by Romanes, because as you might recall, and we discussed this, right? If you want, behaviorism was also a logical consequence of the Darwinian revolution, one of the big ideas that we looked at early on. So do you remember why that is? Does anyone wants to say? Oh no, someone else wants to get in and I have no point. Oh wait, anyone wants to guess why the logic of this transition from Darwin to behaviorism? What were the two main things there? Now, don't confirm my hypothesis that younger generations have no memory, because we talked about it. I was there. Okay, I'll remind you. This is an important transition concept, right? Darwin was talking about adaptation, the survival of the fittest, right? So it was all about to be able to adapt, to be able to learn, if you want, right? So this is one thing that gave huge impetus to the behaviorist revolution, because it was all about learning and adaptation, right? So in some sense, it is a very direct translation of the Darwinian revolution into the study of mind. Because, of course, now we have to study adaptive behavior, right? Then there was this notion of comparison, right? We can compare between animal species because they share features. And the first person who really tried to summarize that is here Romanes, who tries to show how the behavior of a range of different animal species is actually structured around 3 core pillars, right? Reflex, instinct, and reason, and they're mixed in different ways. So this is very explicitly expressing this comparative notion, like, oh, it can be compared now. They share features. Okay. So what followed next was a logical consequence of Darwin's ideas. Yeah. Or Darwin and Wallace, as you know. So, but Romanes, as you see in the quote here, he was basing his observations on anecdotal observations, like people sent him letters. I saw a monkey do something. And that was the impetus for Thorndike to build what he did. Okay, so why Thorndike is so, you know about Thorndike now, you know about his law of effects. A lot of specifics I don't have to explain here, but he was the perfect student because he invented all these paradigms that he built and the puzzle boxes when he was a PhD student at Columbia University, where he said, look, the way people study behavior is plain stupid. This is not science. It's not systematic. Didn't the physicists tell us that in order to understand nature, we have to perform experiments that allow us to replicate? Third person verifiable observe. I mean, he wouldn't use those terms, but that's what he was after. He said, look, I don't care about someone's anecdotes. We need to study behavior in this third person verifiable way. Therefore, I got to build my puzzle boxes, right? So this is actually what you guys didn't mention in your presentation. He actually built the puzzle boxes from packing crates. He went to the local stores where they had packing crates for beans, baked beans. And he used those. He repurposed the packing boxes into these puzzle boxes. Okay, and you know the puzzle box. And then you also know that with that, he invented the learning curve. Although I don't think in the presentation this was mentioned so explicitly. This is the first learning curve ever presented. And you know, we are speaking about learning curves now with ease, and you find it also in common parlance, like, oh, this learning curve is very steep. But someone had to think of that. Someone had to think about that that's a good way to describe behavior, to describe adaptation. And that's what Thorndike gave us, because he said, look, I put the cat in the puzzle box, and I'm just going to measure how long it takes. So now we look at the time it takes, and sometimes the chronometric approach from the structuralists is reappearing. We said, look, I just have to measure how long it takes to solve the puzzle box. And this tells me something about learning, right? And then with that, he had a metric with which he could formulate his laws, right? And now you know these laws. And but what is the law of effect is a very critical one here, and you discussed it. But one thing that maybe did not come out so strongly in your discussion, which I think, however, is really important. What's the difference in the law of effect, as stated here in this quote from his book from 1892, if I remember correctly, the year? What's the difference here between reward and punishment? Think about it. You all look very guilty, at least a few I can see on my screen.
Can you repeat that question? Sorry, what is the difference between reward
and punishment? Just in this quote already. How is reward and punishment different?
Reward leads to satisfying state, and punishment leads to the annoying state.
Okay, but that's sort of a redefinition of what reward and punishment means. But in terms of the learning process in the law of effect.
One reinforces and the other one diminishes.
Exactly, but what's the consequence of that from a perspective of memory? If you are a Thorndikian machine, how is your memory of reward different of your memory of punishment?
Punishment leads to people forgetting things.
Exactly. That's amazing, right? Well, so this is really interesting that Thorndike is very biased in his thinking about learning, because all he focuses on is reward and the ability to retain what leads to a reward. Okay, so and we might understand that, because in terms of his paradigm, the puzzle box, the animal wants to find food, it gets rewarded, and in that process it also stops doing certain things. And Thorndike sees this to stop doing things as a form of forgetting. Okay, but that's a very strong assumption. So and it's also interesting that in modern day versions of machine learning, like reinforcement learning, you still see that same bias. But if we would only remember the things that lead us to reward, we would be dead very quickly, because we also actively learn to avoid things in the world, which is, it's commonsensical, right? You burn your finger. I mean, we can go back to Descartes' example of the boy burning his hand on the fire and learning not to do that anymore. But so always stay critical to these observations, right? There's something missing here. But what's important, this law of effect is still very much with us. So also that same bias is still very much with us. And if we can jump ahead many steps, it actually turns out, if you look at the brain behind me, right? And you see this, the front side of the brain, right? This bit here, the frontal cortex, if you look at what it's doing, a huge amount of its effort is invested in inhibiting things. So in some sense, our advanced intelligence, if you want to call it that, even though we're really capable of destroying lots of things with it, is also based on a large ability to actually not do things, to suppress responses. And that's what Thorndike was oblivious to. But that's fine. This is not to say that Thorndike was not a smart guy who led to a whole revolution, but it was not complete yet. Work had to be done, right? So now what you also have to see immediately, of course, are the important differences between classical and operant conditioning, right? So I don't think that point was made that explicitly in your debate. But if we just look at Thorndike and Pavlov, you could argue that in some sense we have already learned most of what's there to learn about learning systems, because they're two very complementary paradigms, right? And how would you describe the difference between these two paradigms? Anyone wants to make a guess? It's not complicated. You know it. You just have to say it. Think about Pavlov's dog and think about the cat in the puzzle box. What's different already? Just obvious in terms of just the surface features of that situation.
Pavlov's dog is a purely physical response. It's a reflection, whereas the cat is thinking. It's a cognitive agent. Would that be?
It's going in the right direction. I'm not fully satisfied yet, but yes, we're getting somewhere.
Is that the reflex from the dog? Like the unconscious reflex from the dog against the conscious reflex from the cat?
No, be careful with bringing in the C word, right? This is tricky. So it's simpler than this, and you all know it, but you think it's a very complicated thing. But the point is, Pavlov's dog is passive, right? It just stands there, right? And one of you was sort of pointing to this, and stimuli are presented to it. The world reveals itself to the agent. The agent is not active. The agent is a passive receiver of the stimulation. There are sounds and lights, and then there's food, or there's a shock or whatever, okay? So that's also why intuitively people have looked at classical conditioning as a way to discover causal relations in the world, because things happen in certain structured patterns, and you pick up those patterns. If I go to operant conditioning, I'm an agent, I'm active, right? And also you were alluding to this. I'm trying things in the world. So now I learn the causal relationship between my own actions and the responses of the world, right? So in the one case, I'm passive. I learn the causal structure of the world. And in the other case, I'm active and I'm learning the causal relation between me and the world, okay? So these are two complementary learning systems. So, with that, we have the beginnings of the behavioral revolution, as you have discussed, right? Cattell announced this in the early 20th century, like we can build the physics of psychology. And what's important, there's a big ambition to this will be universally true, right? We can apply this to all forms of human behavior. And in the most explicit form, you see this here in these experiments by Watson and Rayner, the little Albert experiment. I don't think this was discussed. But what Watson tries to show here, and of course Watson is one of the big protagonists of the behaviorist movement, is that look, the world can instruct an organism to be anything it can be. It's all a matter of conditioning, right? And what he tries to demonstrate in these experiments, these are classic little Albert experiments, which are considered deeply unethical nowadays. You see here, the baby is not afraid of things. It doesn't show a fear response, right? It shows curiosity about animals. It showed curiosity about the fire. But what Watson does in this experiment, at some point, he will associate, when the baby is with the rabbit, he will make a loud noise behind the baby by slamming on a pot, basically. So this induces a fear reaction. And then he shows that now this fear is then generalized to animals, right? So on the left-hand side, you would see the original response with, in this case, I think it's a mouse or a rat or something. And on the right-hand side, you see the response, you see the crying in frame B3 after the conditioning took place, right? So the point that Watson is making with this is, look, you can be conditioned to be anything, right? This is the infinite malleability of behavior. The world instructs, and through that we can be anything we want to be. And then he would build these kinds of schemes, because he would say, look, the mind as such is in the end different chains, different sequences of stimuli and responses, and we can decipher these because we can condition animals. We can look at how these chains are built. So that means he had the behavior, he had the basic principle, which is still the law of effect, essentially, but now adapted to a more classical conditioning situation. And he has a model behind that where he said, look, the whole mind is built around stimulus-response associations. And that then led him to this famous quote where he says, look, I can build anything, I can build any kind of human being I want. It's all a matter of conditioning, which of course then also was further elaborated by Skinner. But what is important here is that Watson, in this behaviorist revolution, building on Cattell, right, building on the earlier work by Thorndike, they also make a very strong, they take a very strong position against the classic view on the causation of behavior. You will remember that already with Aristotle's 4 different kinds of causation, a goal, right, the teleology of behavior was considered one of the causal factors to explain living systems and behavior. The goal can structure whatever action is formed, or in Aristotelian sense, was also development, right? Development moves towards a goal. But the consequence of the behaviorist revolution and this has had deep ramifications on our thinking about mind and the science of mind, and it's still relevant today, is that goals can be dismissed with. Why is that, you think? Why can we forget about goals? Don't read the whole slide before you answer. Just give me an answer. You guys are not much into gambling, it seems, but you know the answer. But because yeah.
Okay, I was going to talk. Because they are, I mean, regardless of your goal, the goal, which is believed to be the motivation for a certain behavior, is not really the causation of that behavior. What they are showing is that what causes behavior is your previous experiences. So regardless of the motivation you have, your behavior is already set to a path because of what you experienced.
So you go in a direction of determinism.
Kind of.
So you're saying, well, there is no goal playing a role because there's determinism by your past. The past dictates the future. Therefore, your goals don't matter. Is that what you're saying?
That's not what I think,
Oh.
but that's what I think is the, I mean, it's what they were, I mean, that's what I think the answer to the question is.
Okay. All right, I don't agree. Anyone else wants to make a bet? Think about the law of effect, right? Think about the law of effect. In case of the law of effect, right, the world instructs the agent. If I hit you over the head long enough, certain things will happen. So it's not exactly like how you described it earlier. It's more, oops. It is not that determinism is the central ingredient. The central ingredient is the world instructs you. The world gives you the reinforcement that will shape you in what you are. So to explain behavior, I only need to know about the world, and I need to know about your ability to learn, but I don't care about what your goals are because the world will dictate what these goals are. That's the radical. So it's really like behavior as the billiard balls on the table following Newtonian mechanics, right? It's the external forces that make them do what they do. That's why goals can be dispensed with. And for the behaviorists, that's great because a goal is something I cannot experimentally control. So if I can get rid of it, it will strengthen my experimental control. It will build my science in a more valid and solid way. Okay.
Can I ask a question?
Yes, of course.
And are goals really that different from behaviors? Because goals change according to the environment as well, just like behaviors. Like if you're brought up in in a culture that that puts an emphasis on success, your goals might be oriented towards succeeding in a particular, in that context, and be it whatever that culture values. And in this example, it sounds like they're completely different things. It's just goals in this case matter less. But I was wondering if they're really different.
It's a good question, right? Because you're saying, well, maybe goals are like circular, right? They just capture what also the world has told you, right? And as you will see later, this turns out not to be sufficient, right? So it turns out that goals are really have an internal or a dynamics that is internal to the agent that goes beyond what the world can dictate. But this is indeed, of course, now the critical point. Can you prove that goals matter?
Okay, thank you.
Okay. And this is exact. So this is a really important observation you make, because this is now, of course, a line of attack on behaviorism. If you can prove that goals matter, yeah, okay, then with that, you undercut these assumptions of the behaviorist paradigm, like everything is externally defined, right? So let's see. Well, Skinner was, of course, the big protagonist of this empty organism approach of behaviorism, right? That's the fundamental concept here, which we can summarize the whole movement. And you should not underestimate the power and importance of this movement. And that Skinner very much represented as the Pope for many decades, the Pope of behaviorism. It's also when I speak with older colleagues of mine who really grew up as students in the 60s, they were still very much expected to follow these behaviorist routines in the study of behavior, right? So for about 60 years or more, actually, when I started as a student in Amsterdam, they still had cages with Skinner boxes to train rats, right? So in the history of ideas in the study of mind, this paradigm has been hugely dominant. Okay, so it's not just like, oh, you have crazy Watson and crazy Skinner. No, the whole world was doing this. And if you weren't doing this, you had no future. Okay, so don't underestimate the impact of this empty organism approach. And why it's important to appreciate that, you still see the ramifications of it today. As I mentioned earlier, right? Modern day reinforcement learning is essentially mechanizing Thorndike's law of effect. Of course, they became sophisticated about all sorts of things, but conceptually, that's still the core concept. If you go to the literature on addiction, right, where you have a biomedical model of addiction that identifies certain adaptation mechanisms in the brain that would then be affected by addiction, it's essentially an empty organism. The drugs completely, for 100%, enslave the agent, and as a result, they have no more free will. Even though there's a lot of literature that argues against that. Like, for instance, many addicts, if they survive, will actually quit their addiction spontaneously, or in choice situations where you give people alternatives, very often also addicts choose other alternatives if they exist. Just to say, we cannot emphasize enough how dominant this empty organism approach has been and still is, but a bit more under the radar, right? Today, you don't stand up and say, look, I'm a behaviorist and behaviorism is cool. That's not really the thing you put on Instagram nowadays, but it is still an intuition that is there in the practice, if you want, of the study of behavior. Because if you want to say, look, I want to be hardcore third-person verifiable, then almost by consequence, you have to say, well, there's nothing inside because I cannot measure that, right? And that then became also a bifurcation point conceptually, that you had, if you want, ontological behaviorists that said, and in reality, in the real world, this is how it is. There's nothing inside the organism. It's all coming from the outside. And yet methodological behaviorists that say, well, there's lots of stuff going on inside. I just cannot measure it. And that's the whole Tolman, Watson, Skinner debate. And you looked at Tolman, right? And Tolman was very sensitive to these more internal factors and the goals and the teleology of behavior. So Tolman kept on fighting for keeping goals in the picture. Okay, you know about Skinner boxes, so those we don't have to discuss anymore. You've seen a lot of them. But the basic idea would be that, and this is following law of effect, right? If you have a pigeon in a Skinner box that can peck at different targets, it has different behavioral options, but only in one of these behaviors it gets a reward. So now that's the selected behavior from then on. So it's the law of effect in action. But Okay, I don't want to delve too much into detail here. Let me see. I want to jump ahead a little bit because we don't have that much time. We have to catch up with the present. One thing is that what Skinner and his followers then did is to not only look at how that association between a stimulus and a response can be acquired, but they start to fiddle with lots of parameters, right? Because now you can look at, well, maybe if I give more or less reinforcement, more or less food, or I give at different intervals, right? So for instance, Skinner became very famous for looking at different reinforcement schedules, like fixed schedules versus variable schedules, where for instance, you only get the reward every fourth time that you do something. So the paradigm, of course, also created opportunities for many researchers to look at all sorts of details of these paradigms, and for which, of course, you could use the Skinner box very, very efficiently. So let's run ahead a little bit. But now there was one interesting experiment that Skinner performed, and which he reported widely. And in this case, it was actually sort of alerting for those who were prepared to see it, that there might be some problems with this standard paradigm of reinforcement instructing the empty organism, right? So what happened in this experiment, Skinner had the pigeons in the Skinner boxes, and he would give them a reward on a random schedule. Okay, so in this case, so let me see. So the animals would get a reward every 15 seconds, completely independent of the behavior, right? And what this looks at is, of course, whether there's a causal relationship between behavior and food delivery, right? So the reinforcement then is contingent on the behavior. So there must be, let's say, a pseudo-causal relationship between the two to drive learning. Or it's contiguous, it co-occurs in time and space. And what Skinner observed in this experiment is that these animals started to show very highly variable behaviors, right? Some would be bobbing the head, and others would be just making a circle of 8. Others would be just pecking a key. There was huge variability in the behaviors that were displayed, right? And so the point was essentially, these behavioral patterns were what you call stereotyped. So they were like innate behavioral patterns, but it was also highly variable. So that means it was not necessarily instructed by the learning itself, where you might think, okay, I have to pack a key to get the food. But the animals, if you want, were actively exploring a behavioral space. And that's what were called superstition. They then formed a hypothesis of which behavior might lead to food. So that's why it's called the case of the superstitious pigeons. But the doubt that is raised is, is learning then, in this also in the behaviorist case, testing hypotheses about the world? We remember also from Helmholtz, right? Perception is induction. It is testing, it's hypothesis driven. But if the animal would be learning by testing its hypothesis, it's not an empty organism because it has a hypothesis. And that hypothesis matters with respect to the behavior that comes out. So for the behaviorist dream of complete control, this is extremely problematic, as you will appreciate. And this then also translates into our understanding of basic behaviors like, for instance, gambling, right? So, okay, that's the superstitious pigeon. where also humans behind these one-armed bandits in Las Vegas might develop certain stereotyped behaviors in response to random rewards or rewards that are to them unpredictable, but that also would lead them to more gambling. So the superstitious pigeon is not just a curiosity. It creates a doubt about the universality that Cattell promised a few decades before. Like the behaviorist approach is a universal approach to all behavior. Well, maybe not, right? Maybe some behavior is actually dependent on the internal state of the organism. So now so let's move on here to Tolman. You know Tolman now. So there's a lot of detail about Tolman, but we don't have to speak about. Tolman was, if you want, in direct disagreement with Skinner. As you know, you've seen that. And he showed that with some very beautiful experiments, like, for instance, this maze, the 10-hour maze experiment, right? Where he showed that animals form what he called cognitive maps, and that these cognitive maps are global. But he also showed that the learning itself depends on the internal motivational state of the animal, right? You remember the experiment with the hungry animals, the satiated animals, that learning performance varies. But if you switch them, if you go from hungry or from satiated to hungry, it turns out there's latent learning. In other words, I'm learning even when I don't receive reinforcement. Now, this is problematic, right? So now Tolman also built models of this. Oh no, sorry, now I jumped forward. Okay, so Tolman built models of this where I don't have the slide here right now. So Tolman already was thinking about how can he interpret this in terms of an agent. So he actually started to build thought experiments in the form of, let's say, robots, and how these could be controlled dependent on their internal goals, right? So, but the next level up from this kind of theorizing came from Clark Hull, who really tried to build or built a Newtonian physics of psychology that would respect the internal states of the agent. So, and Clark Hull is extremely interesting because Clark Hull was the last person who formulated a single comprehensive theory of mind and behavior. This was the last attempt. So it's important not only that we understand this attempt, but that we also understand why it actually didn't survive, right? And what Hull, first, here we're back very much in Watson territory, right? Where you say, look, a behavior is in the end a sequence where stimuli and responses are brought together. So every little column you see here is a stimulus state, a drive state at the bottom, the D, that's a drive, the thing you want to achieve or satisfy, like hunger. And then there's an action that links them together. And the little box at the right-hand side then indicates the so-called goal state. So basically what Hull is saying, look, all behaviors that we observe are in the end sequences of sensory motor events that are coupled together through the drives that they serve. And then it's the goal that glues them together. So that means if I'm moving through the world and I do something, then I'm in one of these columns. I see something, I have an internal drive, I'm hungry, I'm thirsty, I'm whatever, and I perform an action. And that leads me to the next column that I have in my sequence, right? So he tried to decompose complex behavior in these sequences with these primitives of drives, actions, and sensory states and goals. So what you see here in 1934, at the peak of Skinner's dominance, here we have Hull, who's still pushing for the unifying integrative role that goals have to play to link the sensory motor associations, the stimulus response associations together. But that's only the beginning, right? Because then Hull tries to add specific principles to how these sequences operate. And that also means that indeed you have problems now, right? The single stimulus might lead to multiple responses, as you see in box B. And so he tried to impose principles of operation now of this machine. So what he's essentially proposing, I mean, this was before the computers were invented, right? But these are simple automata of sensory response sequences that would give rise to behavior. But these were, if you want, the representational building blocks of his theory, because he goes a lot further. So let's go here now. This is, if you want, a summary of how Hull would think a stimulus gets transformed in a response. Now this will look like a bunch of boxes with letters and circles. So you would think like, well, this is complicated, and why would I care? Well, you should care about this because Hull is actually trying to explain very concrete behavioral paradigms with this. And what he is formulating is that I cannot explain the behavior we measure without referring to these internal states of the organism, right? So for instance, if you go from left to right, S is the stimulus in the world. Then S prime, which is already rather sophisticated, is saying, well, there's an internal representation of the stimulus. It's not identical, right? The agent has to represent that stimulus in some way. It is transduced. And the V then also indicates that this triggers a certain value. And these combined will lead to what you see in the circles, SIR and SHR. And what these represent are stimulus response tendencies. And they come in two shapes. Inhibitory tendencies, you see, we're already beyond Thorndike's law of effect. We're not stamping things out, right? Hull is saying, no, we have explicit associations with respect to inhibiting certain responses giving a stimulus. So he sees more as a potential, right? So SIR, and then IR, the top circle, will be an overall inhibitory tendency. Am I freezing or am I behaving? Okay, so now we said, look, the stimulus translates in a number of behavioral tendencies that are inhibitory, that are non-specific to the stimulus on the top. That's just whether I'm freezing or not, non-specific, or it's specific, something I learned about the stimulus and the response. And then you see how these arrows come together with ESR in the center circle. And this is now the summation. So look, interesting. No, I'm integrating these different internal representations of stimulus response relationships and behavioral tendencies to say, this is my best hypothesis of what I should be doing. Okay. And that then comes together. That's where the D comes in, and the UR. That's where the unconditioned response elements come in. These are my reflexive responses to the stimulus, and they again get integrated in the next phase. And then after that, I generate my response through a form of action selection. So what is really interesting and curious about Hull, and it is really difficult to read how he describes these models. It's very tedious because every variable that he identifies is really linked to very specific behavioral experiments, right? So it's difficult to decipher, but okay, this is the core model, and this is a very interesting model. And it's very close to how we would build a robot model of behavior. These are the elements you would consider. But Hull was just thinking about this, I mean, this is during the Second World War, in pure abstract terms. And okay, so in your notes you can read the detailed description of this, but it is a very sophisticated way to think about learning, and you see we're way beyond Thorndike here. We're way beyond the law of effect. Now it's not an empty organism. There's lots of stuff going on inside this organism. And what is going on depends on the experience of the organism. There's also a point that one of you made earlier. So Hull is already pointing to the fact that we cannot explain all forms of learning in terms of the empty organism. Acquired states, learning, past learning influences future learning. And that's the key thing here. So, okay, then he does lots of additional things with that. But what happened with Hull's proposal, and it basically collapsed under its own complexity, right? So this is the endpoint of sophistication in psychology. Also, there's no other theory in psychology that came after this that was integrative, that was comprehensive to describe all aspects of behavior. But it fell apart. And why did it fall apart? Well, he wanted to have a framework for psychology as a natural science, right? So that means when he looked at these excitatory behavioral tendencies, I summarized the equation below, SER, so the stimulus exciting a certain response, well, this would depend on a number of parameters. One of them was J, and then J was defined as an empirical variable. That means the gain, right, how rapidly you translate the stimulus into a response now depends on an empirical parameter that I will estimate based on the empirical literature, on the experiments people have done. But then exceptions appear. In this case, the learning curve you see on the right-hand side is showing a learning phenomenon that was just discovered in 1945 by Reynolds. So when Hull was developing the framework, it's eye blink conditioning, right? So in eye blink conditioning, you have a stimulus like a sound, an air puff or a shock to the eye. We'll look at it later in more detail. I will close my eyelid and I will associate eyelid closure to that sound. But then it turns out, and that's what I show in this graph, if the time interval between the predictive stimulus, the sound, and the air puff varies, your learning performance changes. So what this shows is that if I have a time delay between sound, air puff of 500 milliseconds, I can reach almost 100% conditioning. But if it's a bit shorter or a bit longer, it drops down to 70% very quickly. So now this is, for Hull's framework, this became a massive problem. Because how do I now estimate my empirical parameters to control my model? So as a result, so he was adding ad hoc solutions to this, but the more experiments people did, the more regularities were found out, the greater the problem. Okay, so and then the whole framework of Hull collapsed under its own weight, and we still have not recovered. It was a very brilliant theory, but it couldn't be maintained. So this is our big problem. How do we deal from a theoretical perspective in the study of mind with all this variability? Okay. The legacy of Hull, though, is he was still pushing this notion that we can only explain the behavior, that's as far as he could get, when we consider the animal as an active, goal-oriented learner. So now last part, I don't know if Ismail's already in the room or not, or Giovanni, but now I want to bring some of these elements together, and hopefully you have time to explain it. So we talked about eye blink conditioning, right? So this is a typical setup in humans. It follows the paradigm we just discussed. There's a sound, there's an air puff, you see the little tube under the eye. There's a little measurement device that measures eyelid closures, right? So it would really work like there's an unconditioned stimulus. So we're in the Pavlovian regime of learning. There's a conditioned stimulus, a sound, right? And then I will see the eyelid, or here's the air puff. I close my eyelid. And now look at the right-hand side, right? Before the training, you will see the eyelid close. So as measured at the moment the air puff arrives, before training, but after training, you see the eyelid starts to close before the air puff arrives. So it anticipates the arrival of this noxious stimulus, okay? And if you increase the delay, then you can get adaptation of this response, right? So in rabbits, you would look also at the nictitating membrane, because the rabbit doesn't only have an eyelid that closes in the vertical direction, it has also a membrane that goes over it laterally, right? So you also can look at the conditioning of the nictitating membrane. And now in pursuing this paradigm, a new discovery was made by Wagner and Savourda, and summarized later in the Raskol and Wagner laws. And this was another nail in the coffin of behaviorism. I don't think you guys discussed the blocking paradigm yet, right? In your debate club. Now you all look very guilty, so I guess you didn't, or you forgot. In both cases, let's go through this again. So in blocking, Wagner and Savourda posed the question, okay, if I look at learning in classical conditioning, so we do eye blink conditioning, right? What happens when I have compound stimuli, and how does the history of my learning experience affect future learning? So in this case, they had 3 groups of 20 rabbits, and the unconditioned stimulus was a shock to the orbit, so a shock to the eye for 100 milliseconds, which of course leads to eyelid closure. And then they had 2 stimuli, right? CSA is a flashing light, and CSX is a tone, a sound. And what they then did is they did first a training on the compound. So we have a flashing light, right? Then we have the sound combined, and I get my shock for 200 trials. That was the same for all 3 groups. But then in the second part of the experiment, either I had one group, group 1, that only got the flashing light reinforced, okay? And the other one saw the flashing light without the shock, okay? And now the question is, what happens when I test these animals on the tone? So the question now is the previous exposure to the light in isolation in any way interfering or affecting the significance I give to the tone? So anyone wants to guess? Or you think this is too boring to even guess? It's super exciting. You young people have to appreciate the importance of this experiment. It is world-shattering relevant. So for group 1, if I test them on the tone, do you think compared to the control condition, group 2, we will see more or less responses to the tone? Or the same?
I don't know, but I'm guessing that if there was like a previous experience with the tone, it would somehow inhibit like learning, like associating the same like the same experience to another, like in this case I forgot the stimulus, but
the A is the light, flashing light, and X is the tone.
okay, so I'm guessing, I don't know, but I think that if there was like a previous exposure to the association with the tone, associating afterwards with the light would be like more difficult.
Mm-hmm. Right.
But I don't know.
Any other guesses?
I think I would agree with Adriana in the sense that there has to be like extinction from the previous conditioning.
Mhm.
So yeah, I agree with her. Yeah, nothing.
Good. Anyone else?
My opinion was the same as Adriana and
Uh-huh.
Denise, but just to make things, well, I'm trying to think how I might be wrong. And perhaps because you already have the conditioned behavior, maybe it actually assists with the learning and makes the learning faster. You just replace the stimuli with another stimuli, but the subsequent behaviors are already learned. So maybe it's even more. I don't know.
But I don't think it's as simple as just replacing one stimuli to
Mhm.
another. Like, I think they would need to be like similar in order to make like a connection.
Mhm.
Because replacing would mean, as Denise was saying, like forgetting the first one and relearning with a second one.
Mhm.
So
Mhm.
unless the stimuli were like really similar, like maybe presenting like two stimuli that appeal to the auditory sense, maybe in that way it would be easier. But like here, I think they're really different, so I think it would be like harder to relearn.
Mhm.
Mhm.
Okay. Any other guesses in the room?
So I am actually, because, so can you rephrase what Ariana said? Because I'm sorry, I wasn't paying attention, but I just want to be sure that is the same as I think.
No, just say it. Don't worry about it.
Oh, okay, bueno. Because I think, so I'm not sure what she says, but the point is that if the stimuli are different, then it doesn't, I mean, I don't think it matters that they are different. I think they are going to be associated
Mhm.
anyway. So for example, with the what you show was on Watson, so he was giving a sound and then when presenting the animal, and then they two became the same. It was the fear for the animal.
Mhm.
So I think those two are going to be associated, and then
Okay.
I mean
All
the
right.
sound with the blinking eye.
So let's take a look. I don't know if you already see the slide now because I'm struggling with appearing windows. And here we go. This is the result. And this was the world-shattering observation, right? So if we do the test with X for group 1, right? So group 1 got extra sessions training with the visual stimulus, the flashing light. And you see relative to the control group, right, the response to the sound is diminished, right? And if you now go to the group 3, where they had additional sessions with the flashing light that was not reinforced, you see this, the response to the sound is enhanced relative to the control group. So why do you think this was called blocking? Okay. So this was summarized in the famous Roscola and Wagner laws of associative competition. And it basically says animals only learn when events violate their expectation, right? So if we now go back, in this case, right, you would say, well, if I get sound and light combined reinforced, right, and then I get only the light reinforced and not the sound, then for me the sound is not predicting stuff, right? I don't, so it's not relevant. If I get more of the light reinforced, okay, that violates my expectations, so I learn about it. Similarly, for the light not reinforced, that's now a surprise. I just have been reinforced with it 200 times in the compound with the sound. And for a behaviorist, these Roscola-Wagner laws are, of course, an unmitigated disaster. So why do you think that that's a disaster? It's really, it's where we started today and where we're ending now in the 70s. We start with Thorndike's law of effect, and now we have blocking. So why does this blocking phenomenon show you that the law of effect is incomplete? That the empty organism is incomplete? It's you know it, okay? And you have to answer right in front of you. Because
So-
in the rest, sorry, go ahead.
No, I'm so sorry. Yeah.
No, I want to hear you. Tell me.
So maybe the previous stimuli effects like this previous stimuli effect continues in the present or the future as well. So even though I'm like, when I speak, I'm still trying to actually like process the result and like still trying to conceive, like understand the topic, but maybe the effect is still, even though it is still existing today and the future performances, but like we can still sense the other stimuli, but in the sense that they are actually not, they're competing with each other. So there's like I don't know, like the cognitive capacity is, I don't want to say diminished, but it is used. I don't know, like.
No, definitely you're going in the right direction with that. Absolutely. So in the Vescola-Wagner model, which summarizes a lot of these experiments, right? There are two elements. First, you say V is the association between a stimulus and a response can comprise compound stimuli. So if, for instance, sound and light, that's the top, they just add up. It's a sum, right? That's one thing. So associations with one response are the sum over all the associations that response has with all possible stimuli. That's one thing, right? Which is interesting, right? Because it means it's additive now. And then they say the change in the association, that's the second statement, second equation, the delta VI. So the change in association with stimulus I depends on some parameters like alpha, which depends on the properties of the stimulus. For instance, how salient, how bright is the stimulus, how easy is it to detect, right? Or gamma, which depends on the response we're looking at. And then it depends on lambda minus the sum over all the associations that already exist. So this is extremely, because they say, look, lambda is now a ceiling, an associative ceiling. Right? So if I want to learn about a new stimulus, I first determine how much, if you want, associative space is still available. Because the sum J over Vj is the sum over all associations that already exist. And if that sum is equal to lambda, there's no more association space left. So that's why they speak of associative competition. And with that, they explain blocking, right? Because if the light, the flashing light, is perfectly predicting the outcome, then V light is equal to lambda, and my associative space is 0. Right? So in these very simple equations, they explain the blocking effect, and which can be then summarized in this more intuitive sense that animals only learn when events violate their expectations. But what did Thorndike say? When it leads to a satisfying state of affairs, it's stamped in. Vescola and Wagner say, no, only when it's not expected. When it's expected, there's no learning. But if you are Skinner, Watson, Cattell, and that whole crew, this is the moment to just retire, right? Why is that? Because the organism structures its own learning. You see, we have recovered agency. The agent matters. And this is absolutely needed to explain this empirical fact of blocking. It's fantastic, isn't it? So now within an hour, we have seen, there are other examples, we have seen some very fundamental limitations of this behaviorist paradigm. And that the organism matters. The organism structures its learning. This was known in 1972, and we still don't know how to include that in our theories about mind and brain. But this is the beginning of the entering a new paradigm where the internal states, if you want, the internal cognition of the agent is of critical importance to understand how that agent learns and how mind is structured. Isn't that fantastically exciting?
Excuse me, it's similar to the paper in which the babies had a logical situation, and when they created a hypothesis of the outcome, and when it did not match, they fixated on it like more time. It's similar to this one. No, it was like from 4 or 5 weeks ago.
Ismail, can you help me out here, or Giovanni? I don't have the reference properly.
Yeah, hi. I think it was the first experimental paper, right? You're referring to?
I don't think so. I think it was the 3rd or 4th. There was one with a language, not that one, but one with a situation in which they put something on a box, then they covered the box and showed up.
It's the precursors of logical reasoning.
Yes.
Right.
And it was something like this. When they did not expect something, they like looked at it more time.
Okay, cool. Now that would match, but then that's more an attentional effect, right? And indeed, actually, this is extremely interesting. You mentioned this. After Rescola-Wagner models the model was presented, there became a whole discussion in the field of the study of learning, where it said, indeed, it's an attentional effect. So it's not affecting the learning itself. It affects how the agent is sampling its inputs, exactly how you describe it. So this indeed is so very, very good observation. You're absolutely right.
Although in that paper, like the point was that like infants were forming some sort of expectation, and then the events were violating like some logical consequence of that expectation. And that was so. I'm not sure in there they were like stressing much that although then what they were measuring was some sort of like attentional effect. So like they were measuring fixation. But I think that the whole point there is that like infants has some sort of like internal state, first of all, internal set of expectations, and that they could perform logical reasoning around that.
Right, but then the overt measure is an attentional shift.
The overt measure is an attentional,
right?
Yeah.
And so, and what that leads to, which is really relevant in this discussion, it is true that there are attention-oriented interpretations of the blocking effect.
Yeah, right.
So Rescola-Wagner is an associative learning interpretation, but as you are alluding to, indeed, there's a competing interpretation, which is purely looking at how you sample input relative to the violation of your expectations. So definitely relevant observation. So this is cool. And then we will continue with our trajectory into the future next week. I know I'm way behind, but it's fun as we go along, and we still have a few lectures in front of us. So thank you all very much for joining me today here. This was fun, and thank you all for participating and your suggestions. And then I guess we have a short break, and I'll hand over to Ismail and Giovanni for the debate club. Thank you.
That's right.
Sorry, Paul, is there time for one more question?
Of course, no, sure. For me, there's always time for more questions, but it just eats in your debate club time. This is more
Maybe I,
Well, it's eating in the break. let's
in the
say.
break.
So
Okay, so then
just go ahead.
Go ahead. Yeah.
okay, I'm gonna go ahead. But if people want to take breaks, I guess maybe it's not interesting for everybody. So please take the breaks. This shift of emphasis from rewards to expectation, to me, it rings very analogous to the role of dopamine that, or the understanding of maybe dopamine and neuroscience as, if I'm understanding correctly, it used to be sort of the feel-good chemical, but now it's more thought to be, it correlates to the expectation of a reward, not the
You're right.
reward itself. And I was curious if you think this is like a case of the tail wagging the dog, where the findings in neuroscience is made to fit this a shift in sort of behaviorism to this Riscola and Wagner and the emphasis on expectation, or if there's or if you think it's sound science. Can any analogies be drawn, or is it like a different?
No, it's extremely interesting. So absolutely, look, it's really interesting that Wolfram Schultz, when he discovered this, he wasn't thinking about Riscola Wagner, right? He was just doing experiments with his monkeys, and he saw that these dopamine neurons are very sensitive to the violation of their reward predictions, because the dopamine neurons in the ventral tegmental area have, let's say, a baseline firing rate, and they fluctuate around that baseline dependent on the absence or presence of reward. So it fits perfectly with the concept of Riscola Wagner. However, the first evidence about how the brain implements this looks at a very different structure. That's the cerebellum. And I wanted to spend some time with it next week, but then what I promise I will do, I will also include the dopamine story on reward and reward prediction. So you can see that link for yourself. And what I want to achieve with that, and of course I make big jumps all over the place. In 72, this was really a very important nail in the coffin of behaviorism, to say, look, the agent matters, okay? And now in the late 80s and 90s, we actually understood how the brain does this. We really know now the substrate of that's regulating in this prediction-based way, at least part of the classical conditioning phenomena that is captured in blocking. So that took another, let's say, 20 years, but now we know. And that's, I think, very beautiful. So I really would like to spend a bit of time on that next week, as we also move on, of course, from behaviorism into the cognitive revolution that also you guys now are sort of chewing on.
Okay, thank you.
Is
I'll
that
wait
cool?
for the next week.
All right.
Yes.
I'm sorry, I have a question. So at the beginning of the lecture, you compared reinforcement learning systems to Thorndike's like law of effect.
Mm-hmm.
And later when you mentioned Hull's theory, it seemed to me like that seems much more similar to reinforcement learning. So there's an agent, and there's a stimulus, which is like the states, and then there's a response, which is the actions, and you map stimulus to response through this policy that is shaped by the agent's experiences in the past. So I'm just confused on where to put reinforcement learning in this whole thing.
Now, look, reinforcement learning is also evolving, right? If you look at deep reinforcement learning, we also look more at learning the state space, and then you learn the policy. So it's also, of course, evolving, which is a good thing. But I would argue it is slowly evolving in the direction of Hull. But the standard is very much Thorndykean, that you would just say, look, I have to optimize my reward function. So whatever doesn't optimize it, I should just forget about. These are not states I want to associate with my response, right? So in that sort of boneheaded textbook form of reinforcement learning, we're still very much in the Thorndike side of the discussion, right? If you look at the whole component, for instance, you look at excitatory and inhibitory components that are both learned and that are competing. Well, I've not seen any reinforcement learning models even worrying about that, right? Except Ismail's. So, but you see, so I completely admit that they're evolving, but they're still too much at the Thorndikean side of things as far as I'm concerned. Yeah.
Thanks.
But Paul, I think that's kind of like maybe the difference between model-free and model-based reinforcement learning, right? Would you agree with that?
Not completely, because also in the model-based. So, okay, now you have to explain this, Giovanni. Now you opened Pandora's box.
Yeah.
And so model-based and model-free essentially is a distinction that Peter de Jaan proposed with Daw 20 years ago almost, to say, well, if you look at, for instance, certain forms of learning, like classical conditioning, it's a very instantaneous association between a stimulus and a response, right? So it's very direct. It's here and now.
And doesn't probably require like some internal state either. Right?
Exactly. It's not dependent on any kind of internal computations. Well, if I look at operant conditioning, I have to have internal models of the world. I have to make predictions. I have expectations. So I need a model. And I can use my model now to think about different policy scenarios about which I can learn. So that became this distinction, model-based, model-free. And a few years ago, they wrote another paper where they say, well, we don't really believe in this distinction anymore. So, okay, well, thank you very much. But however, also in the model-based case, the value function you optimize through positive association. They don't care about acquiring negative associations that would prevent you from optimizing that function, right? And that will be the big difference from my side. So that's in a nutshell my bastardized version of model-based, model-free, and how it still fits in the Thorndikean school. And this is the moment for Giovanni to disagree.
No, I agree with that.
Okay, great.
No, honest, I don't have a strong opinion, but it's like for me, it was more like the necessity of having like an internal state or not, right?
Yeah, but you know,
so when you look at the goal of effect of like a pure like simple associative learning, like you can just avoid like to have like internal representations, right? But
yeah, but you know, I would bet that all.
So for me, that's a big difference.
That all learning is model-based. It's just that the models vary in complexity. Look at the cerebellar learning, where you have the parallel fibers already tuned to the periphery, to the time constants in the periphery. That's model-based, and that's the simplest form of classical conditioning, right? So, so I think it's a caricature that hasn't helped us. But I know that this is a little bit nerdy detail, but for most of the participants in the discussion. So I've been looking at it quite a bit also when we're dealing with the whole addiction discussion and so on. And it's okay. I think it's a useful caricature to try to categorize forms of learning. But if it comes down to it, in the brain, it's all model-based.
I mean, it's also computational abstraction, right? Like, I mean,
of course,
when we look at the algorithmic implementation, you can clearly like define a difference between the two, right?
Yeah.
But I tend to agree that like probably everything kind of boils down to at least a very, very simple model or internal representation.
Yeah, exactly. All right, look.
So now that we agree,
yes, we do.
Now that we agree, it's the moment to stop.
Exactly. Better end on a high. You know, we end on a high.